Welcome to The Explainer. Today we're diving into an incredible engineering mystery that literally makes modern air travel possible. How does the heart of a jet engine, surrounded by a raging inferno, keep itself from having a catastrophic meltdown? It's a wild story of extreme forces and materials pushed to their absolute physical limits. It's a question that just seems to defy all logic. Because the inside of a modern jet engine is one of the most hostile environments we humans have ever created. And the most critical parts are spinning right in the heart of it all. So to really get a handle on just how big a challenge this is, we gotta look at the numbers. Okay, picture this. As that super hot gas blasts out of the combustor, the temperatures hitting that very first row of turbine blades can spike to 1,500 degrees Celsius. To put that into perspective for you, that is way hotter than molten lava. And this is where things get completely wild. The temperature inside the engine is actually hotter than the melting point of the metal alloys that the blades are made from. I mean, just think about that for a second. How can a solid object survive, let alone do its job, in an environment that should turn it into a puddle? And on top of that insane heat, these blades are living through what you could only call a symphony of destruction. We're talking 12,500 revolutions per minute, with the blade tips screaming through the air at almost 1,900 kilometers an hour. The centrifugal force trying to rip them off is immense. It's like hanging the weight of 2 double-decker buses from each individual blade, all while hot gas is trying to eat away at them. So really, how is this impossible feat of survival even achieved? Let's start peeling back the layers of genius, starting with the core material itself. All right, our first clue to solving this whole mystery isn't just about what the blades are made of, it's all about how they're made. And it's a process that has a lot more in common with growing a giant gemstone than it does with traditional metalworking. So here's the deal with most normal metals, even the really strong ones. On a microscopic level, they're made up of tons of tiny little crystals, or grains. And the boundaries where these grains meet are natural weak spots. Under extreme stress, it's kind of like old Velcro. The individual hooks and loops are strong, but the connection points are where it all starts to fail. So what's the solution? Well, it's just breathtakingly clever. Get rid of those weak spots completely. Engineers figured out how to make an entire turbine blade that is one single, giant, perfectly aligned crystal. No grain boundaries, no weak points. The material strength at these crazy high temperatures just skyrockets. Yeah, you heard that right. They don't forge or cast these blades in the traditional sense, they literally grow them. They pour this molten nickel-based superalloy into a special mold and cool it down so precisely that it solidifies from the bottom up, forming one continuous, flawless crystal. It gives the blade unbelievable strength. Okay, so we've got this perfect crystal, but even that isn't enough to survive 1,500 degrees Celsius all by itself. And that brings us to the second layer of defense, which, honestly, is maybe the most surprising part of this whole thing. Hidden deep inside the blade. If you just look at one of these blades, it seems like a solid, beautifully sculpted piece of metal, right? Well, that is completely an illusion. Because the truth is, it's hollow. I mean, look at this. It's filled with this incredible, sophisticated maze of tiny passages and channels. The blade isn't just a blade. It's a highly complex heat exchanger. So this hidden plumbing works by siphoning off some air from the engine's compressor section. Now, don't get me wrong, this air isn't cold by any stretch. We're talking 600 degrees Celsius. But hey, when the outside is a searing 1,500 degrees, 600 is practically chilly. This air constantly flows through those internal channels, acting like a radiator and pulling heat away from the core of the metal. Okay, let's recap. The material is a perfect crystal. The inside has its own cooling system. But we still need one last, totally invisible defense. Think of it like a force field protecting the blade from that furnace of hot gas rushing right past it. And this external shield is actually a really clever two-part system that basically creates an invisible bubble of protection around the blade's surface. First up, you've got something called film cooling. Some of that air from the internal plumbing is strategically bled out through thousands of these tiny, laser-drilled holes you can see on the surface. This creates a thin film, a little cushion of cooler air that clings right to the blade, acting as a barrier that the hot gas has to fight through before it can even touch the metal. Now for the final layer of defense, well, the best way to think about it is with a dessert. the baked Alaska. You've got that fluffy meringue on the outside that's full of air, and it perfectly insulates the ice cream inside from the heat of the oven. Well, the engine needs its own version of that meringue. So that meringue, in an engine, it's called a thermal barrier coating, or TBC. And it's this special ceramic layer. Get this, it's only about 1/4 of a millimeter thick, but it's such a fantastic insulator that it can drop the temperature the metal actually feels by over 150 degrees. It's the ultimate final heat shield. So let's just take a step back and appreciate this. A single crystal structure, internal plumbing, a force field of cool air, and a ceramic heat shield. It's just an absolutely incredible combination of technologies. But, engineers, they're never satisfied. They're always pushing for more efficiency, and that means even higher temperatures. So what's next? Well, the next frontier is a whole new class of materials called ceramic matrix composites, or CMCs. These things are a real game changer. They're made by blending silicon carbide fibers with a ceramic matrix, and the result is a part that's way lighter than the old superalloys and can handle even higher temperatures with less cooling needed. The manufacturing process for these is unbelievably complex, but the payoff is absolutely huge. See, if you need less air for cooling, you can use more of that air for thrust. And that means one thing: more powerful and way more fuel-efficient engines in the future. I mean, when you really think about it, from growing a perfect crystal out of molten metal to wrapping it in an invisible shield of air, the modern turbine blade is nothing short of a masterpiece. It operates so far beyond what its own materials should be able to handle, it really makes you wonder, if we can solve this, what other impossible problems are we going to solve next?